welcome everyone. Today I'll be talking about pushing particles on an unstructured grid. So we've picked up another project we're quite excited to be working on, and I guess part of this is to help me digest what I've been learning. But as you do things in research, it's important that we share with each other what we're learning, because if you don't share it, then what's the point? What's the point? We're all here about expanding knowledge. So, anyways, yeah, we'll talk about. I want to just give some context here about like why we're looking into this, so you have an idea of what it is we're up to, and then of course we'll get into some of the details here. So the project we're involved in, I guess through a few layers, is really housed underneath what's called the Warm World Project. This is a project that is funded primarily by the Federal Ministry of Education and Research in Germany. There's three main overarching goals of this project, and a lot of them are focused around a model called ICON, ICON. Now, ICON is it's my understanding that this is like an atmospheric weather code. It's a climate modeling system that allows interaction between ocean and atmosphere and land components. Very similar to the frameworks we have stateside with the Earth System model that's developed at NCAR. The difference with ICON compared to previous models that have commonly been used for oceanographic and weather modeling is that ICON is an unstructured is a code based on unstructured grids. In past, the workhorse models that have been used have all been finite volume, and they've been traditionally based on unstructured grids. So this is a bit different. But as you go down this realm of adopting new codes that have new data structures, particularly those that take into account unstructured grid topology. All the post-processing tools that we were using previously with structured grids are not necessarily valid. So as there's more adoption towards unstructured grid models, we need to spend some time adapting a lot of the post-processing tools that are available to researchers to make use of unstructured grids. So I did mention ICON. I'll just go ahead and leave a link to the repository there. But again, yeah, ICON it's a flexible, scalable, high-performance modeling framework for weather, climate, and environmental prediction. Key takeaway and the relevance to us here is that it uses unstructured grids. Another code that's involved in this project is called FESOM. The FESOM code, much like ICON, is based on unstructured grid, uses primarily triangular cells in 2D. And the vertical level on the ocean side, you just have stacked layered cells. So early versions of FESOM were based primarily on finite elements. FESOM 2, which is the one we're currently working with, uses finite volume method, and there's a various arrangement of staggerings of where the velocity components are located relative to like temperature and stuff like that. So we'll talk about that here in a minute. And then the last bit, this is actually where most of our work is actually involved, is with the OceanParcels code. So OceanParcels is a Python toolkit. The parcels actually stands for probably a really computationally efficient Lagrangian simulator. The idea behind OceanParcels is that you can take general circulation model output from an ocean simulation and use the velocity fields and the temperature, salinity fields, etc., to move particles around based on forces that you can put in as a user very simply. Of course, the obvious thing you can do is if you have velocity fields on a mesh, you can use those to push particles around. If you want to simulate things like plastics and things like that, you need to understand like what the temperature salinity is, so you can calculate buoyancy forces, among many other complicated things. Now, OceanParcels was primarily written with the idea of what was state-of-the-art models at the time, which is basically Arakawa A grids, B grids, and C grids. So again, all structured GCMs were assumed, and we've been brought in to help adapt OceanParcels to understand unstructured grids, so that you can still do particle simulations with the next generation of ocean models. Yes, I've left 2 links here. You can I would highly recommend you check out oceanparcels.org if this kind of thing is up your alley. Even if it's not, it's pretty cool to see the sort of capabilities that researchers have at their disposal to study things like how trash moves around the oceans, things like that, or other kinds of drifters or floats. It's quite a neat project. We're very excited to be a part of it. So yeah, let's move on to the next bit here. So I want to introduce the concept of the problem that we're going to do, thinking only about two-dimensional space. We'll talk about structured grids, so I can kind of lay out what we need to have done in order to do this on unstructured grids. I have shown here is a graphic that shows 2 different types of grids. We have an A grid. Let me see if I get my laser pointer on here. An A grid, which if you were to divide up all your space into a collection of points and have some understanding about like the spacing of all these points, you can basically do finite difference, finite volume on that. On an A grid, the way the variables are staggered, if you're solving the Boussinesq equations of motion, remember you have velocity components and you have tracers like temperature and salinity, or passive tracers, those kinds of things. All of those values are collocated with each other when you're using an A grid. Now, if you're on a C grid, the way those are done, it's a little bit different, is you would put the x components of your velocity on the east and west faces of each of your cell. You put your meridional component, so the component of the velocity that goes north-south, on the north and south faces of your cells, and then your tracers are at the center. The C grid is quite nice because it has some nice properties for easily getting second order accuracy, for ensuring that you have a divergence free flow. It's quite a popular framework to use. Particularly here, you see here we have a code called Nemo that uses C grid and MIT GCM. But when you have this whatever mesh arrangement that you choose, A grid, C grid, or the Arakawa B grid, which is a little bit less popular, you have velocity values at fixed locations. And if you want to do a particle simulation, what you need to be able to do is figure out which of those points those particles are near, so that you can do piecewise interpolation onto those particle values. On a structured grid, especially if it's uniformly spaced, that's quite easy. If I have an XY position for my particle, I can divide by the grid spacing value and get back I and J indices for the U and V for the nearest points. And then you can use that information to very quickly do interpolation onto that particle point, so you can advect it around. Now, of course, when you're on unstructured grid, you can't just do that because the elements are laid out in a bizarre way. And so you need some way to reference back to this. But essentially what the approach that I'm going to be taking to this, I think, is that we're going to use this kind of indexing. So if I can overlay on top of an unstructured grid a structured grid like this, and relate particle positions to that structured grid, and I can relate particle position, the unstructured element positions to the structured grid, then I can create little simple lookup tables to quickly interpolate onto, or at least do my element search to find which elements my particles are lying within. So that was kind of an overview of where this is going. I basically, this is the end of the slides here. I'm going to jump into a Python notebook that kind of walks through all this stuff. Now, this notebook, I do have a link to it down below. Let's see here. Let's get VS Code up. So this notebook you can find online. This is in that in the description of this video, github.com. This is on the Elphi WW. So again, the Warm World projects. One of their repositories. There's a repository called Unstructured Mesh Parcels Sandbox. If you wanted to dive into this in a little bit more detail. But essentially, we think about this problem of how you push particles around in a mesh into 2 stages. You have your particle positions as an input, and then you have all your mesh connectivity information as another input to this. And what you need to be able to do is, from your particle positions, figure out which elements in your mesh that particle is inside of. And then once you have that, you need to do some kind of interpolation from the velocity points for that element onto that particle. So if you think about it in 2 ways, we're going to first just talk about the element search. How can I figure out the element ID that particle is inside of? I've summarized at the top here. I won't go through all of these in real detail. 7 common methods for doing this for both structured and unstructured grids. The first one we've already talked about is that direct grid indexing. Again, particularly if the elements are your grid is uniformly spaced, you simply take the particle positions, X and Y values, you divide by the grid spacing, and you take the floor of that, and that gives you the index of the nearest point to the south and west of your current particle. Pretty quick, pretty easy to do. The complexity on that is order 1. I mean, if you for each particle, it only takes those 2 calculations every time. When you go into unstructured grid, there's quite a few options out there. A lot of common ones I've seen show up in like I think it's Pangeo's PyG interp. I think that was what it was. You'll see like quad trees and KD trees are commonly used for these searches. Basically, it uses the mesh connectivity information to coarsen up the mesh to some degree, so you can do searches that basically you have a check that says, am I inside a polygon or am I outside a polygon? And if you coarsen up your mesh, you can ask that question on some really big cells. And then once you know where you're at in the big cells, you go 1 level down, and you figure out where your particle might exist, inside of a higher resolution grid through your quad trees. Anyways, we're not doing those. The deal is the KD trees, quad trees, the bounding volume hierarchies, and Voronoi diagrams, they're all scale like order log n in complexity, meaning that if I have a larger mesh, it can take more time for the same amount of particles. What I really like doing, and what we're going to be talking about today, is spatial hashing. This is, again, an order 1 query. We basically relate everything back to a structured grid. If I have this fictitious structured grid underneath everything, I can relate my elements to that, and I can relate my particles to that, and then match them up, basically, and do my searches that way. There's a few steps here. I did summarize them up above. We'll look at a few graphics to make it a little bit easier to understand. But if you did want to read all that, you can. So what we're going to do first is look at a very, very simple problem. Here we've got a square domain, right? And we've got these red dots are locations for our corner node vertices for the grid, and then the blue lines outline each of my elements. I have all these triangles in here. And then thing about unstructured grids is there's no unique way to order this. Like I could label this one element 1, this one element 2, 3, 4. It doesn't matter. What matters is if I have a list of nodes, I can then take from that list of nodes and tell you what that element is based on which corner node IDs there are for that element. If you find elements that share an edge, in other words, they share 2 corner nodes, you know that they are neighbors with each other. This is called connectivity. This is all the kind of information that you start with when you have an unstructured grid. So, all right, that's what we've got. Now what we want to do in order to do the spatial hashing is we want to overlay on this unstructured grid a structured grid that is much easier and faster to index. As we said before, if I can relate particle position to a structure grid by just dividing by the like a grid spacing size and get an index out of that, that's pretty quick to do. So let's scroll down here again. All these things, if you wanted to play around with this, you can. I want to go down to this plot here to show you what I mean. So this figure here is showing the same unstructured grid that we were looking at before, but now I've overlaid on top of it what I'm going to call my hash cells. That's my structured grid where I can do all of my indexing. So this guy, it does kind of go past a little bit the extent of the original domain, but that's not a problem. But you can see here I've got 2 indices for each hash cell. I have an I and I have a J. The I's vary from left to right, And if I give you an I value, I can just multiply that by the hash cell width, and I can tell you the position of the lower left node. I can then also derive, if I wanted to, the position of the lower right node, or the upper left node, or the upper right node. And now what we want to do is, if I have this sort of setup, one, if I look at a particle on here, it's very easy for me to reference which I and j that particle is associated with. And then if I were, visually looking at this graph, we can see that, this bottom triangle here is associated with a number of our hash cells. So if I find a particle, for example, is in hash cell 0, 0, and I look in another table and say, hey, this element here that has these 3 corner nodes is associated with hash cell 0, 0, I want to be able to go through that element and do a check quickly to see if it's inside of there. This is nice because if I didn't have this hash cell representation, what you might think you could do is just, I'll just go through my entire list of elements and check, is my particle inside or outside of this element? And that certainly would be inefficient. So anyway, so this is just again, problem setup here. We've got our unstructured grid. We've got our structured grid, our hash cell grid underneath that. What we're going to try to do now is relate the unstructured mesh elements to those hash cells. And essentially what we do to do that is if I construct a bounding box around each triangle. So like if I were to again look at this guy in the lower left corner, his bounding box would extend from 0, 0 to 0, 1, and then up to y equals 1. And that bounding box is going to contain hash cells 0, 0 through 2, 2. And so that's just one way we can relate this. This is what we're doing in this example here is we just look at the bounding box of the triangle and we count up all the hash cells that are inside the bounding box for each element. And so we can create a lookup table for each element that relates the element ID to a set of hash cells. And of course, because we're doing this process, we can get the inverse of that as well. So if I give you an IJ, I can tell you the list of element IDs that overlap with the list of element IDs that are associated with each hash cell. That's essentially what this function is going to be doing for us here. And I think, let's see what I got next here. So there's a few things you can play around with inside of this. I think the sizing of your hash cells certainly is a free variable here for you to play with. Like there's no reason that they had to be this small. Typically what you want to do is pick your hash cells so that they're roughly as big as your smallest element, at least in terms of their area coverage. And if I recall correctly, that's the criteria I'm using here, is that we just look through the unstructured grid, calculate the area of each triangle, and take the square root of that to get out a length scale. And from that length scale, we use that to set the delta X and delta Y values for the hash cell grid. But that's, I might have scaled it a little bit because they do look kind of small. At any rate, all that choice does, changing the sizing of your hash cell is going to change how many triangles are going to be associated with each hash cell. What I have shown below is a histogram for this particular setup that shows how many triangles are associated with each hash cell. So there's 35 there's 35 hash cells that have an association with only 2 triangles, 17 that have an association with 4 triangles, and 2 of them have an association with 8. Generally, what you want to see for this kind of thing is you want to have as few triangles to search through. So if you give me an IJ, the likelihood in this case that I'll end up with having to search only 2 triangles is quite high, because the majority of the time, a hash cell is associated with only 2 triangles. If I happen to be unlucky and land in a hash cell that's associated with 4 values, then I might have up to 4 triangles to check, and God forbid you end up in this edge case over here. Again, these are all just like tunable parameters and things that you can check before you start doing these kinds of particle pushing, but definitely playing around with that ratio of the hash cell size to the element size is going to influence the distribution of that histogram and change the efficiency of your search. Ideally, again, you want to have basically all of your hash cells being associated with as few triangles as possible. Okay, so at this point through the process here, we have our unstructured grid. We've created our hash cell grid, and I've now associated each hash cell with a list of triangle IDs. So you give me an I index, you give me a J index, and then I can tell you the list of triangles that you're gonna want to search through to see if a particle is inside that triangle. And this is where that order 1 complexity is now coming into play here. You can see that no matter what, I have a fixed number of triangles to look through for each ij value. And again, calculating those ij indices is as simple as dividing the position of your particle by the grid spacing of the hash cells, which is quite fast. It's just the integer arithmetic there. Okay, so now what we need to do is align particles with the hash cell. So what I'm doing here is just seeding some random particles on our grid. We'll take a scroll down below. So now what we're looking at is the same picture as before. So we have our unstructured grid. Again, red dots are the corner vertices of our triangular cells. Blue lines are each of our triangular elements. In the background, we have our hash cells, right? So I varying from left to right, J varying from bottom to top. And then now what I've overlaid on here are some random particle positions here. I've got, what is that, like 8 of them, 10 of them? Yeah, 10 of them. I see P0 all the way up to P9. Okay, so now I've got these random particle positions. And what visually looking at this, you can tell, because you're a human, which elements these are in. But we need to be able to communicate to the computer how, because we have our elements stored according to what their corner node vertices are. We need to be able to relate this particle position, for example, P0. Let me actually try to zoom in on this guy because this is kind of small. There we go. P0 to this particular element. We know he's inside here just from looking at the picture, but of course, in practice, these are much more complicated. And the way we're going to do this is we're going to take the X and Y position of P0, and we're going to determine which hash cell it's in. Now, from this picture, we can see he's in hash cell 3,1. And then we're going to use those ij indices for the hash cell to then get the list of triangles we want to look through and then do a check to see if he's inside of that element. And that's the other magic behind this I need to explain. I've been kind of dodging that at this point. But we'll do this for each particle. Again, particle position, we'll map it to a hash cell ID, so an ij. We take that ij, we put it into our other lookup table to get a list of triangles, and then from the list of triangles, we want to do a check. Am I inside the triangle or am I outside the triangle? So, you may or may not be familiar with something called barycentric coordinates. And this is quite a useful calculation to be aware of. But essentially, if you have 3 vertices of a triangle, this applies to any n-sided polygon, you can express a coordinate inside of that triangle as a weighted average of those 3 vertex points. And it turns out that the weights that you use, the illustration I'll give you here is that, let's look at P0. If I make a triangle from this lower corner node to P0 and from P0 to the other corner node to my right, that subtriangle has an area. And I can then make another subtriangle that goes between the lower left node, P0, and the upper one. That gives me another triangle I can calculate an area of, and then I get an area from the remaining triangle. Those fractions of area, so if I divide each of those subtriangle areas by the total triangle area, those give me weights. Those weights happen to be what are called the barycentric coordinates. So I can take the area, the fractional area multiplied of the triangle span by these 2 points multiplied by the corner node, plus the fractional area of the other triangle multiplied by this corner node, and so on and so forth to figure out how to express P0 as a function of those three vertices. There are criteria for those barycentric points. For example, the barycentric coordinates have to be between 0 and 1. If you find that you calculate this and any of the coordinates are outside of that range 0 to 1, you know that point you're looking at is outside the triangle. The upshoot of this as well is if you have the barycentric coordinates, you have what you need in order to do at least bilinear or trilinear interpolation. I guess that would be bilinear because it's 2 dimensions technically. At any rate, you have what you need to do linear interpolation if you calculate the barycentric coordinates. It's kind of what I like about it, just out of the gates. So you can have your interpolation method for free, and you get a consistency check. Am I inside or outside of the triangle? And then you can make your decision about whether you continue searching through your hash cell lookup table list. All right. So that's basically what's going on there. I think we're nearing the bottom of this thing already, which is kind of cool because it feels like I learned so much, but I like it when it feels like I learned absolutely nothing by the end of it and I just need to keep going. Yes, that's basically the bottom of it. So I guess I'll summarize here what we did is the gist of doing this on an unstructured grid comes down to an element search followed by an interpolation. And the interpolation part is really what you're using to put velocity fields or buoyancy fields onto the particle position so you can calculate forces, how you're going to be pushing your particles around. To do that initial search, what we're doing is using a fictitious structured grid that underlies our unstructured mesh. We relate the elements to each of those hash cells, so I can give you can give me an I and a J index on my hash grid, and I can give you a list of triangles you might want to look through. And usually that's a very short list. In this particular case, we saw we had some hash cells that had 2 elements, some had 4, some had 8. And then once you have your particle positions, you relate those to an I and J index, and then from the IJ index, you get your list of elements to check in, and we use barycentric coordinate calculation to determine if you're inside or outside a cell. Again, check out that Python notebook up online at the LVWW GitHub organization. It walks through all this stuff. You can play around with your own mesh if you want to make bigger meshes, more particles, etc., to get a feel for how this works. I guess I'll make a plug for a few things. One, if you have any questions and you're hanging around here live, drop your question in the chat. If you don't see a chat window, that means you need to subscribe. Only subscribers to this channel are allowed to participate in the chat. I'd love to hear from you here if you have any questions. I'll hang around here for a minute. Next week, we're switching gears again. We're going to go back to some Fortran stuff. If you're a repeat listener, you know I've been doing the F word recently again, which has been a lot of fun. But next week, we'll be looking at various ways to calculate vector divergence using a spectral element method on CPUs, on GPUs, etc. And we'll show you kind of what we learned through a number of benchmarks, what performs the best on modern GPUs and multi-core CPU platforms. So that'll be fun. Not a lively bunch today, but that's all right. If you do have other questions, you can always reach out to me at support@fluidnumerics.com. I'll drop that in the chat here. Yes, that's support@fluidnumerics.com. I'm always happy to talk shop with people who are doing research, doing CFD, physical oceanography stuff. If you do cloud-based stuff, I love anything. I love hearing what you guys are doing. Boy. Why'd you go with this method of finding the particle element? Yeah, this is I guess there's the motivation here is spatial hashing is it's got order 1 complexity. What that means is for each particle, I always have a fixed number of elements that I need to search through. So if I increase my mesh size, the amount of work I need to do to implement this method stays the same. And there's a caveat to this is that the initial setup is where all the cost is. So basically, once you have your hash grid defined, which is easy, you just give me a hash cell width, delta x, delta y, and a starting point, x0, y0, and I can tell you any point in that grid just off of an integer index. That's pretty fast. And then you just need to relate your elements to that hash cell. That's like the most expensive part, but you do that once for a fixed grid, and you can reuse that over and over for any number of particle arrangements. The other methods we looked at, so quad trees and KD trees are order log n. If you're not familiar, maybe you are familiar with quad tree, KD tree, but those basically use the connectivity information of your mesh to come up with coarsened representations of your grid, so you get larger and larger polygons in your grid to search in, and you do a similar thing like we're doing like with the barycentric coordinates for arbitrary polygons to determine, hey, is the particle inside or outside the coarsened guy? And then once you know which coarsened part of your mesh you're in, you look at the next level of the KD tree or quad tree, and you kind of can continually go down to the mesh resolution that you're at. Those again they're nice, and a lot of people implement them. I've seen them everywhere in oceanographic codes. Again, Pangea's PyInterp, I believe, does this, and there's another one, UX Array from the folks over at NCAR. They do quad tree, KD tree. Again, it's great. It's fine. It works well, but again, it scales order log n. So as you go to higher and higher resolutions, it gets more expensive. Where again, spatial hashing, which is funny enough, I saw that was predominantly used by the plasma physics people. It hadn't quite made its crossover to the oceanographic and meteorology communities quite yet. But spatial hashing is order one. I mean, it's fast. It scales well, because everything comes down to doing stuff on structured grids underneath and then doing a lookup table. The other benefit there is it's probably going to allow, like when we go to implement this inside of OceanParcels, which is the ultimate goal of this project, I should be able to reuse a good deal of the structured grid framework they already have and just add this additional lookup table. So my hope is that it's not too much of a change to a lot of the software that they have, and it's really just a type extension that adds this extra step to do a lookup table search for the unstructured bit. But I guess those would be my famous last words before I actually dive into coding it. So, John, I hope that answers your question, and I also hope it opened up more questions. So if you got anything else, man, let me know. I feel like I ought to put some elevator music on this stream. It might keep the air from going dead. So collisions for spatial hashing. So we don't actually use a single hash index. I know a lot of people will calculate a hashing based off of the two indices, but if I've got two indices, I and j, there's not really a collision. So if I have an x and y value for a particle, if I divide by delta x from the x position, and I divide by delta y for the y position, that gives me the I and j index for the lower left corner hash cell that I'm inside of. So there's no collisions there. However, once I have an I and j, I could have multiple triangles I need to look up. And I think, at least in this example, it is something in practice we're going to have to be careful of, I believe. Let me see here. Blah, blah, blah. Where's my histogram? I have a histogram. There's my histogram. Yeah, so like in this dumpy example, I have 35 hash cells that are associated with two triangles, 17 with 4, and 2 of them with 8. Like that result is a function of, really two parameters, delta x, delta y of your hash grid cell, if you assume that your unstructured grid's kind of a given. So yeah, like Yeah, okay, so cool, that makes sense. So I guess I did answer the question on the collisions for the hash lookup. Yeah, so I just use IJ, but if since I will have multiple triangles per hash cell, like there's just kind of you do brute force yourself through this of like, all right, calculate barycentric coordinates for each triangle in my list, but again, majority of the time in this example, I'm going to be landing on two triangles to look at, so that's not too bad. And ideally, you know, when we do the pre-processing to set up these kinds of grids, we're probably going to be looking at these kinds of histograms to see how expensive the search is going to be for a given setup. So, yeah, I don't know. It'd be cool to figure out ways to automate this to like optimize this histogram during the setups, like pick your hash cells accordingly. There's other cool things you can do. I mean, one thing I saw a group do. Let me see if I can find where's my plot with the particles on it. If you want to like reduce the total number of elements you're looking over, there's a neat thing you can do where is like every so often you can calculate a bounding box of your particles with a little bit of a buffer. And like, I mean, this is probably a bad example because my particles span the entire space here. But like if you had like your particles clustered in a spot on a very large grid, it probably wouldn't make sense to create a hash lookup for the entire grid. Instead, what you might do is like, oh, my particles are inside of such and such bounding box. And so I'll just create a hash table for that. And then every so often, I'll probably want to figure out a way to like rehash everything. But you know, you don't want to do it every time step, but you know, you could do those kinds of things to really speed stuff up is just like use spatial locality of your particles to reduce your search space. So yeah, these are all kinds of things I'm interested in, but like really my goal is keep the complexity low, keep the code fast so that there's not a whole lot to do, and then try to leverage a lot of the infrastructure that's already in place in OceanParcels since they're coming from structured grid. I think this will be quite nice. John, man, you're awesome. Thanks so much for asking the questions. If there's anything else I can answer for you or anyone else here, pop your question in the chat. Again, if you don't see the chat, subscribe to the channel. If you subscribe to the channel, I think I have a timer on it. It's like 2 minutes. Once you've subscribed for 2 minutes, you're able to chat. So I'll hang around. If you like what we're doing, give us a like. We like seeing likes. Who doesn't like seeing likes? This was a quick one today. Yeah, I guess I'll do my plug again next week. Next week we got a few things going on. We'll be looking at vector divergence with spectral element methods in Fortran. Should join us for that if you want to see how to compute vector divergence fast on multi-core CPUs on GPUs. That'll be fun. I've got someone lined up in a couple weeks to talk about some of the work they're doing with like turbo machinery and combustion fluid combustion codes. I'm in the midst of trying to understand sort of what he's doing these days, but he'll be on our channel soon. Really looking forward to that. That'll be fun. I'll keep you guys posted when we get that. That might be a pre-record, so that might just get posted. And if you're subscribed to the channel, you'll get a notification about that. Oh yeah, if there's anything you guys want to see in this realm of like numerical methods, conservation law modeling, stuff you're interested in, let me know. Drop a something in the chat or in the comments below this video. I'm always keen to understand what you guys are interested in, what projects you're doing. It's nice to do things that are relevant that I also get excited about, and basically numerical methods, physical oceanography, CFD in general. That's my jam. I love doing this stuff. Well, I've been rambling for the past few minutes. I'll let you know. I think we're gonna go ahead and call it. Thanks for tuning in, and I'll see you guys next week.